So welcome back to the explainer. Last time we made sure everything fit perfectly in the 3D model. But today we're tackling the harder constraint, the absolute most unforgiving boundary in all of offshore engineering. I'm talking about weight. If you're building a multi-billion-dollar asset, getting this wrong is literally a project killer. So let's jump right into it. To really wrap our heads around this, we actually need to break our terrestrial bias. You know how we're so used to building things on land? On land, if a building design gets a little heavier than expected, well, it's a pretty easy fix. You just pour a thicker concrete slab right, maybe dig a deeper foundation, or bring in a bigger crane. Space and foundations are negotiable. But offshore? Offshore, weight is buoyancy. And buoyancy is absolute, non-negotiable physics. If you exceed your weight limits, your asset simply doesn't float at its design draft. There is no bigger crane to save you. There is no thicker concrete slab. Once that steel is cut, you absolutely cannot buy your way out of a weight overrun.
Because that buoyancy factor is just so critical, we have to track two very specific numbers continuously, starting from day one of the project. The first metric is LWT, or lightweight tracking. This is basically everything that is permanently welded or bolted to the asset. Think of it like the unmoving skeleton and organs of your project. We're talking hull steel, major equipment blocks, process piping, electrical cabling, all of that. Once it's on the asset, it stays on the asset.
Now, the second vital metric we track alongside all that permanent steel is VDL, which stands for Variable Design Load. If LWT is the skeleton, VDL is the lifeblood of the asset's operations. This captures literally everything that moves, everything the platform actually needs to do its job out on the water. Process fluids, diesel fuel, heavy drilling consumables like mud, spare parts, and, the actual personnel living and working on board. Both LWT and VDL are tracked in a live weight register, and they have to be reported monthly without fail.
And here is the relationship that catches people out. It's a terrifying zero-sum reality. Because the total displacement of the hull is a fixed physical limit, every single kilogram your lightweight tracking grows silently destroys a kilogram of your variable design load capacity. Let that sink in. If the engineering teams let structural steel or piping weight grow unchecked, you're actively reducing how much fuel, how much drilling mud, or how many critical spares the asset can actually carry offshore. And the truly scary part? Operations usually only discovers this fatal constraint years later, out at sea, when they physically can't load the supplies they need to function.
Think about it like a long-haul aircraft. Say an airline decides to add heavy luxury seats and elaborate espresso machines while the plane is still sitting in the hangar. Nobody really notices the weight then, right? But because the maximum takeoff weight is totally fixed, every extra kilo of cabin fit-out is a kilo of jet fuel the plane can no longer carry. That means lost flight range. Everyone definitely notices when the aircraft can't actually reach its destination. Well, an offshore asset is making the exact same zero-sum trade. It's just measured in lost operating days offshore instead of lost flight miles.
So what exactly do you do when project maturity inevitably reveals a weight overrun? Well, you're forced to run what are called lightweight reduction proposals. And let's be clear, these are a formal, ranked list of strategic deletions. They are not simple, tidy little design cleanups. In real-world deep-water programs, recovering a blown buoyancy margin has meant striking out things like forward anchor winches and their thousands of meters of associated heavy wire entirely, just gone. That is a deliberate, massive operational capability being traded away purely to keep the asset floating safely at its design draft.
Let's put this into a real-world scenario. Imagine you're sitting in the project manager's chair. Your latest weight report hits your desk and shows that your light weight is 400 tons overweight, and you are already at 70% design maturity. Decision time. Which painful button do you press? Do you just accept it and hope for the best? Do you quietly cut the variable design load allowance, robbing your operations team? Or do you run reduction proposals?
Well, you have to run reduction proposals. But the hard, uncomfortable truth here? The real answer is that you should have caught this massive overrun way back at the 30% model review. At 70% maturity, fixing a 400-ton problem is violently expensive and disruptive. See, weight control is not a singular event. It's definitely not an emergency meeting you hold when you realize you're already sinking. It is a rigorous, daily discipline you run from day one of the project. Or, I promise you, it will run you.
To wrap up this explainer, let's look at the core outcomes. In Part 1, we saw why you needed those model maturity gates, and now you know the two crucial weight metrics, LWT and VDL. We've seen their absolute zero-sum relationship, where LWT growth actively destroys your VDL capacity. And we know what a lightweight reduction proposal actually costs the operator out in the field. It's not just a tweak on a drawing, it's a loss of real capability. So, I want to leave you with a final, provocative thought to consider for your own projects. If you aren't rigorously managing your permanent steel weight today, what critical operational capability are you secretly deleting for tomorrow?